Ready for crazy? All right, so one of the first big problems you tackle in calculus has to do with this velocity problem. So the idea of how quickly is an object moving at any given time. So like if I drive to Anchorage, is my velocity constant? Probably not, right? Because there are places like Nenana where there's a speed trap and you must slow down to get a ticket, right? And Litter Gulch, where you probably also want to slow down and not kill those poor tourists who come in and infuse our economy with money, right? So the question that we're asking is how fast is something moving at a particular instant? And it turns out that that's the same thing as a tangent line. So first question is, what is a tangent line? So suppose you have a curve, and the curve might describe my speed as I go to Anchorage, so it goes up and then it goes down, then it goes back up, something like that. Okay, so there's my time, and here's my speed. No, time versus, never mind. I'm not going to give any labels because I'm trying to think through what I'm talking. It's not a great situation. So a tangent line is a line that touches the curve and has the same direction as the curve. Or it's the line you see when you zoom in super close to your point. So I'm not sure if you play with calculators for fun, probably not, because you're not like, you didn't grow up when I did and you have phones to play with instead of calculators. But if you were to say graph something on a calculator or an app on your phone and repeatedly zoom in on that function and make your window smaller and smaller and smaller, eventually that function is going to look like a line. Does that idea make sense? If you zoom in super, super close, you're going to get things that look like lines. And so the tangent line is the equation of that line at a specific point. So like here, the tangent line would look like this. It's the line you get when you zoom in really, 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 really close on that interval. So it's going to preserve the same general shape and general direction, like that line right there would be increasing. If I zoomed in right here, the line would be decreasing. And that tells you information about how is your particle moving at that point in time. Might be going forwards or backwards, something like that. Okay, so what is the problem with getting an equation of a line? So here's the question. Can we find an equation of a line with just one point? Is that possible?
No, the line could be going in any direction, right?
Yeah, so when you think back to Algebra 1, what did you use to find the slope? How many points did you need? 2. And so the problem is you need 2 points. So problem, we need 2 points. Crap. Okay. So, well, is there a way, so a common theme in this class, and actually Calculus 2 as well, and probably even Calculus 3, is if you can't solve a problem, find a way to get something that's really close to the answer using an estimation technique. Does that make sense? That would come up in life too. If you can't solve something exactly, why don't you estimate it, right? So I'm going to draw and put another slide so I can draw. So let's pretend that I have this curve, and I want to find, it's got something like this, and that's my point. And we're going to call that point P. It's got some x, f of x coordinates. Okay, so find tangent line at x equals, at x comma f of x equals to p. What if you found a point that was close? So pick a close point, like over there. Does that make sense? Can you find the slope of an equation of tangent line now? Yeah. So pick a close point, and we're going to call that point, I don't know, let's say another letter, z, f of z, we'll call that point q. Close point q, and find the slope with p and q. And q could be less than, q could be a point that's to the left of x, f of x, or to the right of x, f of x. How could you make your approximation better? Oh, you can use derivatives, yes, we don't know derivatives yet. Okay, we're getting to why we do derivatives. But, so if all you know is, okay, I can find slopes of lines, I pick these points P and Q, does it make sense that the line will get closer to the actual tangent line if the points get closer together? And that's how you make it better. So you make it better by making P and Q closer together. In other words, you send the letter Z towards X. Does that make sense? If Z gets closer to X, then those points P and Q are going to get closer together.
Take the limit of z as it approaches x.
We're taking a limit as Z approaches X. And so one thing we're going to talk about is how to deal with expressions like this. We're going to find limits. What happens as things get close together, but maybe not quite all the way there. It's kind of like that zooming in process. Zooming in closer and closer and closer involves making your interval smaller and smaller and smaller and smaller. Okay? So let's do that with a specific equation. And if you've taken Calculus 4 on your written homework, you cannot use derivatives yet. Okay? On WebAssign, I can't tell what you're doing, so do whatever you want. But I mean, I'm just saying, on the written homework, you're only supposed to know what I've taught you so far. Okay. So find an equation of the tangent.
Wasting our time then?
No, because we will do this for exactly like 3 or 4 days, and then you can move on, okay? So I'll waste less of your time. But the idea that we're trying to, this is not just me, it's everywhere, is that you're trying to point out that this is the meaning and where these things come from. It's not just like,
I believe you, I don't need.
you don't know calculus yet. You can't know the tricks and rules without first knowing the theory, like this part of the theory, because they all come from this. Okay, so find the equation of a tangent line to this parabola at the point 1, 1. Okay, so first let's graph that parabola, just roughly. Goes through 0, 0, 1, 1, 2, and somewhere up there. Okay, so the tangent line will look something like this. Okay, and so we're going to estimate this using the point 1, 1 and some other point. So like we'll call that point Q. And I don't know Q's specific coordinates, so it's going to have some x. What's its y value going to be for some x? Some x squared, right? You get the y by squaring the x, that's what the equation is, right? And then we're going to find the slope of this line. So we'll just do a couple and we'll guess what the slope should be. Okay. So what's a number a little bit bigger than 1 but close to 1? How about just a little bit bigger?
1.1.
1.1, that was my guess, but 2 is also bigger but kind of far away. So let's pick 1.1. Find the slope. Okay, so if the second x is 1.1, what's the y gonna be at that point? So m was y2 minus y1 over x2 minus x1, right? So it'd be 1.1 squared, which is 1.21, minus 1 over 1.1 minus 1. Does that make sense as an idea? We took one point that we have is always going to be 1, 1. That's the point we care about the tangent line at. The other point is the x and y coordinate of the nearby point. The nearby point's x is 1.1, its y is 1.1 squared. If you put that in a calculator, where do you need parentheses?
Around, yeah.
Mm-hmm. There and there. So that gives you about 2.1. Yep. Okay, what's an even closer number than 1.1?
1.01.
1.01. Exactly. So the point is you can get closer and closer and closer, picking things that are closer and closer to 1. And so this next one, we do 1.01 squared minus 1 over 1.01 minus 1. And I think that gives you 2.01. So what do you think is going to happen when you plug in 1001? You get 2 zeros and then a 1, right? So what do you think this is getting, this m is getting close to as these x's get close to 1? It's getting close to 2. So as x goes to 1, m appears to go to 2. Now, one thing we gotta be a little teensy bit careful about, just a little bit, is those numbers that we chose were all bigger than 1, and maybe picking numbers bigger than 1's a little bit more special than picking numbers that are less than 1 but close to 1. Does that make sense? So like, what would be a number that was close to 1 but a little bit less than it?
0.9.
Yep. And if you do the same thing, you do 0.9 squared minus 1 over 0.9 minus 1, you get 1.9. So in the first case, the numbers were a little bit bigger than 2, but getting closer to 2. In this case, the numbers are a little bit less than 2, but getting close to 2. Does that make sense? And you can kind of guess that from a picture that the slope of that red line is a little bit of an overestimate, as in too large. If I drew it like this, the slope is not steep enough. Does that make sense? But the point is that as the x's go to 1, the slopes go to 2. So 2 is the slope of the tangent line. And for now, this is how we're going to estimate them. We're going to estimate them by plugging in numbers that are close to the value that we care about. Okay, so now that you have the slope, can you get the equation of the line? You could use y minus y1 equals m times x minus x1, right? What goes in for y1 and x1? 1 and 1. What goes in for m? 2. And if I don't specify to solve, you don't have to, so that's good enough. You could say,
Your estimated one.
oh, your estimated ones, you would do the same thing. It's just you'd use 2.1. But the thing is, you use the estimates, and those are called secant lines when they go through 2 points. Tangent lines just go through 1. It's not related to the secant function, okay, but they're called secant lines. But you're not asked to get equations of those, you're just asked to use those estimates to estimate what the slope is going to be. So there's no need to find equations of lines for every single one of your estimates. Yes, yes, my watch tells me to move periodically. Okay, one more thing, then we'll move on to the next slide. So does it make sense that the slope we were estimating was, so it's y2 minus y1 over x2 minus x1, and that was x squared minus 1 over x minus 1. And the point is that we had P was equal to the point 1, 1, that's our point of tangency, and Q was the other point, x, comma, f of x. That's just a formula that told us what we were doing, right? Take the close by number, square it, take away 1, close by number, square it, take away 1, right? Divided by a close by number, minus 1. And what was happening to x in both of those situations? What was x getting closer and closer to? So we were finding value of x squared minus 1 over x minus 1 as x went to 1. The fancy formal way of expressing that is with a limit. The limit as x goes to 1 of x squared minus 1 over x minus 1 is equal to 2. So what we're going to spend a ton of time doing in this unit is taking these limits and figuring out what happens as your x gets closer to that number, which you should think about as plugging in values that are super close to that number. Does that make sense? What happens when you plug in this number itself? What does the numerator expression become? 0. What does the denominator become? 0. Have you ever heard 0 divided by 0 is not defined?
Yes.
And that's because 0 divided by 0 is not consistently one thing. Like in this case, 0 divided by 0 was 2. Sometimes 0 divided by 0 will be 1. Sometimes it will be infinite. Occasionally it will be 0. So being not definable means that there isn't one thing you can say it is. It turns out there are different sizes of 0, and some zeros are smaller than others. Okay? So never say 0 over 0 is 1 because it's wrong. Okay, so let's talk about finding some limits now. Alrighty, and we're gonna just few of these because I know I'm a little bit stuck for time. So let's just do I and triple I. So you have some point P, that's the point 1, 2, that lies on this curve x over 1 plus x. So I want you to find the slope of the secant lines if your x's are 0.9 and 1.01. So what this is saying is find the lines as your x's get close to 1. Find the slopes of them. So the slope will be y2 minus y1 over x2 minus x1. And this number is the number that you're plugging in for x that's close by. So in the previous problem, we plugged the number into x squared because that was our curve. What is our curve this time? What curve does the point lie on? That's the curve. So this time we'll plug 0.9 into that. That's our second y. So not 0.9 over 1 plus 0.9 minus. Where did that 1/2 come from?
You plug 1 into the formula again?
Plug 1 in the formula. That's why it's minus 1/2. And all that divided by what minus what? What's the second x we had? Say that again? Oh, a little bit careful. So the x2 corresponds to whatever gave us y2. So in this case it'd be 0.9. So I'm just going to say that x1, y1 is the 0.1, 1/2. This number that you're given, that's your x2. And notice that 0.9 is close to 1, which allows you to estimate the tangent line close to 1. With this, you have to be just really careful when you plug it in a calculator. You get approximately 263, about. And that's gonna be, it's an estimate of what your M is gonna be. Okay. All right, so what would your estimate for M be in this one? What would you plug into the numerator? So for the one that's 1.01. How would you estimate Y2? Mm-hmm. Great. And then minus, great, minus a half, okay, over,
Minus half.
oh, the minus 1/2 is coming from the fact that our one point has this as its x, the other point has 1 as its x. Okay, so you have the point 1, 1/2, this point. And the 1/2, the reason that the y coordinate is 1/2 is this what you get when you take this equation and you plug in 1. When you input 1 into that, you get 1 divided by 1 plus 1, which is 1/2. So the fixed point that you know you want to find the tangent line at is 1, 1/2. And the x that you care about is 1, right? So you pick x's that are close to 1, and you've got to find the y's at those points. And the way to find the y's at those points is to plug the particular x into that equation. Does that fix it?
Yeah.
Okay, what's the denominator supposed to be there? Mm-hmm. And that gives you about 0.249. Okay. If you work these next two, I'll tell you what you're going to get. Is you're going to get m equals 0.250, and you get m equals 0.2499. So using those results, what's your guess as to what the slope will be at that point itself? 0.25, exactly. There's no trickery there. Those numbers appear to be getting close to 0.25, right?
One of them landed right on 2.25.
And that one, it did, there were more decimals there, it just didn't display them. But effectively, it did land right on 0.25. So that's the answer for part B. Using the results, guess the value of the slope. And the value of the slope is m equals 0.25. And then part C says to get the equation. What is the point that you use in your point slope form? 1, 1/2, yep. And that's your slope. So y minus y1 equals m minus x1. So y minus 1/2 equals 1/4 x minus 1. So I think that's y is 1/4 x plus 1/4. But the point is you want to find the equation of the tangent line at that value. And so to estimate the slope of that line, you pick values of x that are close to 1 and find the slopes using those points. So this is why they taught you slope in Algebra 1 like it was going out of style, because you have to know how to find equations of lines. So you'll have one point that's fixed, and then you'll have the other point is the one that's getting closer and closer to that point. That's the basic idea. March towards it. Okay. So let's do the same thing, but actually one that talks about something that has real life equations. So we shoot an arrow on the moon because we're cool like that. Okay, and this thing describes the height of the arrow above the ground. So we're assuming you're like lying on the ground and you shoot your arrow and it goes up and then it goes down, right? And that's, as time passes, there's the height. And you want to find the average velocity over these time intervals. So average velocity, if I was driving to Denali, how would I find my average velocity, or on average how fast I was going? I take how far I went, right, divided by time. So I'm going to call this delta H over delta T. You guys seen delta used for change before? So change in height over change in time. So this thing is telling me the first time point, so time 1 to time 2. From time equals 1 second to time equals 1.1 seconds. So how would I find the height at 1.1 seconds? Put 1.1 in the H equation, yep. 58 times 1.1 minus 0.83 times 1.1 squared. And how would I find the time at 1? Same thing with 1. 58, that'd be 58 minus 0.83, wouldn't it? And then what is the change in time? How much time has passed? 0.1, right? That is the same thing as 1.1 minus 1. Notice that's a slope. Do you see what I mean? This is like y2, right? This is y1, right? Over y2 minus y1. I put parentheses where they should go if you're going to punch it in a calculator. You do this, and the estimate is 56.257. Oh, and what would its units be? So time is in seconds. What's height measured in? Meters. So this is meters per second. So at that moment, the arrow's going upwards. How will doing I and triple I be different? Or will they be all that different? They're not going to be all that different. So here the estimate you're going to get is about 56.332 meters per second. And here the estimate is 56.339. Does that make sense that you do the same thing though? The difference here is you're going to plug in 1.01, right? You're going to plug in 1.001. What you're actually estimating is the velocity at the time when t is 1 specifically. You're kind of zooming in closer and closer to 1. Does that make sense? So using that, what do you think the instantaneous velocity is at 1 second? 56.3, maybe 34? Does that make sense? That's my guess. And it is the exact right thing. But if you want to estimate the velocity at 1 second, you estimate the average velocity over a smaller and smaller interval, which is the same thing as getting the slope. Now the last one we're going to do, and it will not take very long, we'll take a quick break, is what happens, what if you just have tables? So you have this tank and it holds 1,000 gallons of water, which is like many tanks in Fairbanks. If it's full, the water rushes out quickly in the beginning, then kind of like levels off and like dribbles out at the end, right? Does that make sense? So this table of values tells you the time and how much water is left in your tank at that particular time if the valve is just open and it's let to flow on its own with no pumps or any other devices. So if P is the point 15,250, so it's that point on the graph, we want to find the slopes of the secant lines when you have T equals 20 and T equals 25. And this will estimate how quickly the water is leaving the tank at over those time intervals. Finds the average velocity of the water in some sense. So how would you find the slope with those 2 points? Okay, so with 15 and 25, or 15 and 20, sorry. Find the change in gallons over the change in time. So what were the gallons at 20?
I don't think this is a linear chart.
It is not a linear chart. It's going to be something more like this.
So will this estimation lead us to the wrong answer?
Don't think so. It's still it's just an estimation. And if the function doesn't, of the parabola wasn't linear either. Right?
Yeah.
So, it doesn't need to be linear. 111 minus 250, what was the change in time? So 5. And that gives you about negative 27.8. Does it make sense that the answer is negative?
Yeah.
Yeah, because the water's leaving the tank, right? Or the level's going down. Okay, how about with 15 and 25? Change in volume over change in time. That'll be, what, 28 minus 250 over, what? Is that one 5 or is that one? So 25 minus 15, it's over 10. So that one is negative 22.2 gallons per minute. Okay, so which of these is a better estimate for the, let's say, rate of change of the water at T equals 15? So which one of those two estimates is a better estimate of how fast the water is leaving the tank at 15 minutes? Why?
Closer to.
Yeah, this one, because 20 and 15 are closer together than 15 and 25 and more could have changed in that time, right?
Less weight on the water, I guess.
Exactly. And another way to get another estimate would be, I think I just said gooder, would have been to use 10 and 15. You could have used the numbers closest to 15 on one side and closest to 15 on the other side. Does that make sense? Use one below, one above, and then you take the average. So, but the point is that you can average the rate of change by averaging, finding the average rate of change using a slope. And that's all it is a slope.
What if you just got 15, 15, put it in that one from the y minus y1?
Uh-huh. Well, but the thing is to find the slope, you need a y2. Right, and there is no, and because this is a table and not like a function, you don't have a function to plug stuff into to get different values out that are closer. It would obviously be better to pick numbers that are closer to 15 than 20 is, but this might be all the data you have. So the best thing you can do is use 10 and 15 and 15 and 20, because that's when you took measurements. Does that make sense? Okay. And then the last question before we break for a few minutes will be estimate the slope by averaging the slopes in part A. So we'll estimate the slope as, well, it's the average of negative 27.8 and minus 22.2, even if it isn't very good, divided by 2, which gives us minus 25. So then the equation because we're using the point 15,250 as our fixed point, is y minus 250 equals minus 25 times x minus 15. And we're just gonna leave it like that, but that would tell you, estimate how quickly the water's leaving the tank at 15 minutes. So, okay, that's it.
It'd been better to use 10 and 20.
It would have better to use 10 and 20, but just, maybe, it probably was my typo that did that.